Hello everyone, I'm back with another easy one, and in this video we'll be talking about the question diameter of binary tree. Now this is an easy one, but it has its own complications, so let's understand what this question is trying to tell us. We've been given the root of a binary tree and we have to return the length of the diameter of this tree. What do they mean by diameter? They're saying that diameter is the length of the longest path between any two nodes of this tree. So what is this length that we're talking about? Let's not talk about diameter. Let's talk about just the length between two nodes. So let's say the length between 4 and 5 would be 2 because it has this one edge between these two nodes and this other edge between 2 and 5. So combining the two, the length is 2. We have to find the longest possible path that can be formed and we have to return its length. Alright, that's basically the solution. They've given us a small hint that this path, this longest path that we're looking for, it may or may not pass through the root. In this example, it may seem like, yes, it is passing through the root, and it is. It may not be true for all the other examples. Alright, keeping that in mind, let's discuss what we have and see how we can solve this. We'll solve this using recursion. Particularly, we will be using the depth first search approach. So we have the same example from Leetcode over here. We will keep track of our answer variable like such. We will initialize it with the value 0. Now, how do we actually reach the value that we're supposed to return? We will do two things. First, for every node, we will be calculating the diameter that is possible if the path is passing through that very node. So we will calculate the diameter for 1, then 2, then 4, depth first search, right? Then we will do the same for this one, and lastly this one. We'll calculate the diameter for each of them. Whichever comes out to be the longest, we will simply return it. We will of course keep updating the value in this variable over here. Question is, how do we calculate the diameter for any particular node? So we will calculate the diameter in such a way that if we are at a particular node, we will take out the height, we will process the height of the tree on the left and the tree on the right for that particular node. We will then add the two together, and that is basically what the diameter is, right? So just to tell you visually what I mean, we have, let's say, 1 as our current node. The height of the left subtree is 1 and 2. The height of the right subtree is 1. That is basically the number of edges on each side, right? And so the diameter over here will be 1 plus 1 plus 1, that is 3. Alright, that is to understand it visually, but conceptually and the way we are supposed to code it, it's going to be a little more complex. So let's see how we can go about it. So we start off by initializing a function. This function will take in a node as an input. Alright, it will take in a node as an input and it will return this height of the binary tree. Alright, this height or the length, whatever you want to call it, I'll call it height for now. It will return the height. And here we will start off by storing two variables. First is for every node, like I said, we have to calculate the height of the left subtree and the height of the right subtree. So let's have the two variables L and R. Let's keep them at 0. Now, we have to check if a node exists on the left side of our current node. We will update the value of L by recursively calling it. So we recursively call it by then passing the left node's value in this function, and we will add plus 1 to it. Why do we add plus 1 to it? Because let's say we are starting over here, we check if this node dot left exists. That is true. We have this node on the left. When we are going to return its height, the subtree's height, what we'll do is we'll check this subtree's height. As you can see, it is 1. So we will end up returning 1 over here, right? But we also need to accommodate for this particular edge. That is why we are adding this plus 1, so that this edge between the node and the one that is being called now can also be accommodated for. That is why we have +1. And of course, we repeat the same thing for the right subtree. Now, one thing to keep in mind over here is that we will eventually encounter a condition where neither of the left or the right node exists. In that case, we will simply return 0. So let's just add that stopping condition to our algorithm over here. If neither left nor right nodes exist, we return 0. Very, very simply. Alright, so let's try to dry run this. Of course, I will add more components to this algorithm, but let's start our dry run process now to see where we are. So we start off with 1 as our input. We pass this to our function. We check if neither of the nodes exist. That is not true. So we go on and check if the left node exists, because if this condition is false, then at least one has to exist, right? So we check which of the two is existing, if one is existing or both. So we check if the left node exists. We go over to update the height of our left subtree. How do we do that? We pass the left node as we discussed. So that brings us back to the top of the function with this node passed as our new input over here. So we go on and check again if nodes exist below it, and we can see that they do. So we check if the left node exists. So we see that it does. So we make this as our new node and pass it recursively once again. And we go down this path because of our DFS approach. So we're going depth first, as you can see. Now it will make sense to you why we're using DFS. So we do that. Then we check once again, do any nodes exist for 4 as our node? The answer is no. So we return 0. We return 0 over here. So L becomes 0, which is returned from here, right? +1, that is 1. So then we check for the right subtree. The same thing will happen over there. So I won't repeat this entire thing and simply return 0 because it is a leaf node and this condition will hit. So R becomes 1. Now we need to calculate the diameter at this particular node, that is 2. This is where we are at, right? We processed the left node, we processed the right node. Now we need to calculate the diameter at 2 to check if this is the longest we have so far. So let's call it CD, current diameter. This will be simply left plus right subtree's heights. So we have 1 plus 1, that gives us 2. Is 2 greater than our current diameter? The answer is yes. So we will update it over here. And why is it 2? Are we sure it is 2? Let's see. We have 1 over here, 1 edge plus 1 edge. This is the diameter that is being formed with 2 as our root node. So it makes sense that the diameter is 2, right? 1 plus 1. So that is basically how we end up processing 2. Now I said that this function has to return height because now we're still processing 2. We are not done with processing the one before it, that is 1. So we have to give the left subtree's height over here to 1 so that it can take that, calculate the right subtree's height and then calculate diameter at its own level. So we go on and do that by returning the height. But what is the height that we're supposed to return? The height returned is simply the maximum of the left and the right subtrees. In our case, that is 1 and 1, so it doesn't matter what we end up returning, we will just return 1 anyway. But if we had, let's say, another node over here, let's say it is 6, that would then make this returned value as 2. So that will be 2 returned over here instead of 1, but that is not part of our current example, so I'll ignore that. It's just to give you an idea about how this process works. So we return 1 over here. So now we are back to 1. So let's reset these values. So L will become what we received from our left subtree, that is 1 plus 1. So that becomes 2. Then we check if right node exists, and that is true, right node exists. So we make a recursive call to it and we go over and put 3 as our current node. We check if any nodes exist below 3, but it is a leaf node, so there is nothing over here. We simply return 0. So that is 0 returned over here. 0 plus 1 gives us 1 as the value for our right subtree's height. So that is what we get over here. The current diameter then becomes 2 plus 1, that is 3. And is it greater than what we have right now? We do. So we will update this value. And then we return whatever we have as our maximum height. In which case 2 will be returned from up here. But since there is nothing really up there, we don't have to worry about that right now. What we need to worry about is once this entire process is complete, we need to return a diameter. And what will that be? That will simply be 3. That is our answer. That is what we're supposed to return finally. So let's check if that is the correct answer. We go over here, we use the same example, and the output, as you would expect, is 3. So that is how you approach this question, diameter of binary tree. In the next video, we will be implementing this. So stay tuned and follow for more.